Scott, can you walk us through a little bit of the anatomy? We know we had our anchor bolts here. It's 2 anchor bolts coming up out of our
Right.
foundation. I understand this is an older system.
Yeah, we're in the lab, so this isn't really a real life situation where we'd be on a footing or a pier pad where we would have actually poured the anchor bolts in with the concrete.
Sure.
When we poured that chunk of foundation. But here we have some female sockets that we drop the anchor bolt into, set the elevation. But it gives you the picture of what it should look like. The 2-bolt layout, that was something evidently in the past with this steel structure that was donated to the program. But typically, it's at least 4 anchor bolts per column.
Okay.
And that's at least. A lot of times you see 6, and then as the structural member gets larger, so do the number of anchor bolts. You can have huge, like take windmills. I think there was like, when we were pouring windmill bases, I think there was 185 anchor bolts around the perimeter of that.
Probably the size of your forearm.
They were huge. They were huge. 3.5 inch anchor bolts, and that was going 10 foot down into the concrete to keep those things standing in that shear load from the wind. And it's the same thing, when we stand stuff vertical in the air, we have to have a good base under it. So what happens is we'll set the column, we'll plumb it up, we'll shim it in this application, and then we'll be able to move on. So what we have here is we have some flat stock that we use in the lab. We have different thicknesses. That way, if you look over at one of the existing columns, you can see how, because we only have 2 points of contact for the bearing of the column, we shim up another 2 points of contact so we can get it up plumb, or at least as close to plumb for setting as we can.
That head goes back to our plumb, level, and square. We're trying to level here,
Absolutely.
and we'll plumb the column both directions.
So we don't worry so much about getting it just exact just yet. So we'll go ahead and set through. You've got to have a little bit of play in the steel to get things in place. Because remember, it's all designed to be, tight.
Yeah, so if we had 2 of our columns set perfectly, bolted down hard, it may be difficult to get a beam in between.
Right.
But with a little bit of that play, we can lean the column, slide the beam in, and draw it all back together.
That's right, because what we'll do is we'll set a portion of the structure, and then somebody comes back, and starts to tighten up key elements to keep it up while we're working. But we really wait till we complete something before we really do any of the detailing. And so that allows it to get up so high. But if you're going vertical several stories, then you have to detail as you go up.
By floor maybe,
Yeah,
or by
and what I
pod.
mean by detailing is, it's kind of an industry term. That's getting everything bolted up. Your shop drawings for the steel are going to give you all the parameters of how these connections need to look. So what I mean by that is that a lot of times the bolts are just there to put it together as we're going up.
Sure.
It does serve a purpose to bring the 2 together, and it's good enough to keep that, but we will go ahead in most instances, and at least 3 of the sides will have a fillet weld. So we'll weld both of the structural members together at that point. Okay, around those connections.
If it was a bolt connection, the specs would give you like pounds
Yes,
of torque.
we may need to put 45 pound on the bolts, so 45 PSI, which is pounds per square inch, and we use torque wrenches for that. So a torque wrench is like a socket wrench, but it's, I don't know how it operates per se, but it'll catch the socket and it doesn't break until you attain that 40, 45, whatever the structural engineer says these bolts need to be connected at. And then sometimes we'll even go and spot weld the nut in place as well.
Sure.
So that is what I mean by detailing. It's finishing all the welding and the connections, making them 100%. We'll weld, we'll prime those welds so they don't rust, which is very important. And after we get the structure up, that's when we come back in and and I guess before we permanently, I should say I'm getting the cart in front of the horse.
Before
which I often do.
detailing.
Yeah, so before the detailing, we're actually going to come in here and square the building up. And we use certain equipment. We use cabling, come-alongs, which is like a big ratchet, strap ratchet that will, pull the building from top to bottom the way you need it to go. And then we'll use our T16 optics. We would set up out here on an offset point. So this far in the semester, we've done building layout. You guys know what offsets are. So we would set up on an offset, and then I could shoot the line, the plane of the building, for plumb this way, set it up the other way. And so we can plumb the building north, south, east, west. And then once it's in place and we've got all the cables secured, then we'll come back in and we'll weld everything in place.
So just like we had practices when we were doing horizontal controls, where we were setting up, we could check our 90-degree angles with the 3, 4, 5, and we had all these checks. These controls are now vertical controls. We're looking at the building leaning north, south, east, west, and we can pull that building where we need it to go.
And so we can use that at T16 is perfect, because remember, it shoots horizontal angles, but it also shoots zenith angles, right? So I can shoot up and down and see the plane, So what we do is, that offset may be 2 foot off of the building line or the column line, and then I'll have somebody up at the top with the tape measure coming off, and then I will set up over that 2 foot offset, pick it up down line, and then I'll raise my scope up and see what I'm reading on their tape measure.
Sure.
And then we'll adjust the building until my line of sight is smack dab on that 2 foot offset mark up top, and I know that that's perfectly plumb. I like to use optics better. A lot of iron workers, contractors will use plumb bobs if the structure's not that, and that's just usually a brass teardrop. It looks like, inverted, and you can transfer points vertically due to gravity.
Sure. So when we were in our wood structure, we had plans and specifications. It's no different when we're building steel. We have a blueprint of our steel structure. We have column layouts and column lines, a roof framing plan, a floor framing plan. So that's how we know where these pre-built sections of steel are going to go. We can look at our column lines. We can look at the north. In this case, we have a north indicator on our blueprint. That way we know which way we're oriented in space, and we can start picking up our details and know that column A1, you can see that the column's been labeled. So we would know where to place column A1 in the line, and then also our beam layout as well.
Right. So the thing to remember about structural steel is not only are we working off structural prints, but we're also looking at shop drawings, right? So we know all the pieces, parts, where they go, and how they fit together. Because once we get into production mode and we're setting steel, it has to be a finely oiled machine. So
shop drawing is merely the close-up of each individual member, where we can see the bolt hole pattern. We can see any details that would be necessary to identify those beams, because maybe it was mislabeled, maybe it wasn't labeled at all. And with the shop drawing, we can see the connection points. We can double check and make sure we've got the right piece going into the right spot.
So when we look at things, you can see we have, in the steel, we have all these holes blown through the steel. And when we go to the shop drawings, we can start to see what the dimensioning of these holes are. So when we're checking steel, we know what we're looking for. It's got locations of angle iron clips that are welded onto beam members. All of this is knowledge we need to make the setting process go as efficiently as possible, right? So when we're checking steel off the truck, we're looking at what it is, so that we can arrange our steel off the trucks to our setting patterns.
Yeah, you don't want your first piece buried in the bottom of the pile.
Right, so what we mean is when the truck pulls up, I've got these shop drawings, I've got a bill of lading, I see what pieces are coming off, and see, I've already, in my pre-planning phase for the project, I've already decided how I'm going to set the building.
Right, and you have your lay down area where
Right.
the pieces leave the truck.
So we call them a boneyard usually in commercial construction. So if somebody tells you to go to the boneyard, you're going to where all the materials being stored, trailers are out there, work trailers, whatnot. But you're going to go out in the boneyard, you're going to organize it so that the very first piece of steel that you're going to set is closest to the job.
Sure, sure.
Right? So it's a constant process. Well, what I've always done, I should say, is we work it out with the fabrication company. I tell them what my set pattern's going to be, and they'll load the trucks. So the first truck I get is the last steel I'm going to set.
Right.
Right? So the last truck I get's the first steel I'm going to set. And you certainly want to do that if it's just-in-time delivery, meaning we don't have a boneyard, we're working in downtown Indianapolis, and we're building a 20-story hotel.
In that case, you're pulling right from the
I'm
truck.
going to pull a truck up, swing the crane in, the guys are going to start setting steel off of.
So the sequencing is vital.
Crucial.
Makes perfect sense. Let's talk a little bit about the anatomy
Okay.
of the column, and then we can get ready to set.
So these columns are what's called a W8 by 10. So you see a W8 times 10. And so the anatomy, that's what we're talking about anatomy when we're talking about the W8 by 10. And what the W stands for is a wide flanged structural member or I-beam, and that's what we have here. You've got, if we looked at from a bird's eye view, it just looked like an eye.
Okay.
So the W stands for wide flange.
So that W tells us something. We may have multiple
Right.
types of steel out on the site.
Right, you've got all different types of steel. We've got angle iron, we've got, hollow box tube, we've got bar stock, we've got all these different things. So usually we designate it with some sort of letter designation that represents shape.
So that's what our W is for.
Yes.
Now what's that next number? You said 8?
8. So 8 is going to be not the width of the flanges, which is what most people want to think width. When we set that up in a horizontal position, they want to think that that's the width of the flange, but actually it's the depth of the beam. So with our beams, from flange to flange, out to out, is 8 inches.
So that's W is the shape.
Shape.
8 is
The
our
depth.
depth. And this is very similar to the I-joist we talked about in the floor system. That I shape is very, very strong.
Absolutely.
So we have a flange, and then the web in between.
Right.
Okay.
And then the 10, the last number, actually designates weight per lineal foot of the steel.
So lineal 8 or 10 lineal foot.
No, 10 pounds per lineal foot of steel.
So W8 by 10. Why would we be concerned with the weight?
When we procure steel, we actually pay by the ton.
So you're not buying, in lumber, we buy usually board foot, but we also just buy by the stick or the piece.
Right,
So in steel, we're buying by weight.
Right. So if we're paying a package to get this structure fabricated, it may be $900 a ton, whatever it works out to be, right? But we have to know the weight of the structural member for 2 reasons. One, so we can estimate the job,
Right.
right? And we can procure our steel. But also, I need to know how much this particular column weighs if I'm going to hang it from a crane. If I'm going to use a crane to place the steel, it's crucial in my rigging practices how much that member weighs. So we have a 14-foot long column, and we know that it's 10 pounds per lineal foot. I know that that column weighs 140 pounds. So knowing that that weighs 140 pounds, then I can go and I can choose the rigging that I'm going to incorporate into the lift. And the rigging are the lifting straps or the wire rope chokers that we use setting steel, because they all have a weight designation.
Okay.
They only have a maximum amount in a certain rigging configuration that it's allowed to lift. Okay, so we need to know the exact weight of the member going up.
So that W8 by 10 tells us everything we need to know.
Everything we need to know through that. Yep, absolutely.
And then we have a base plate at the bottom of our
Right.
column. That's our anchoring point, and the holes that you talked about before. These were put in during the manufacturing process to match our beam layout.
Right, absolutely. So all these, and because they're blown through the holes, we have to utilize, our shop drawings to make sure that the fabricator's right. Air runs rampant. Human error runs rampant through our industry, and it happens.
So we can check our shop drawing versus the actual versus the bill of
Right.
lading and keep cross-checking to make sure we've got the right piece in the right place.
And really, if you're doing that process off the trucks into the boneyard, you're saving yourself a lot of hassle. If we do it up front of the job, as we're unloading and stacking material and getting ready to get things going, if we're making sure that all this steel is the way it's supposed to be, we're money ahead.
Yeah,
when
because
we're
if we're
setting.
trying to do it during set day, where we may have a very expensive crane, an expensive crane operator, and
Absolutely.
lots of manpower standing around, and we didn't catch that error early, now we're just burning time, and that's money.
Yep.
So we'd use our prints to also know the configuration of the column or the beam, because if we'd spin a column, you may throw off the bolt pattern.
Yeah, right. So if you look at this column, we're on the outside of the structure. So this would be the outside of the building. We have a steel beam that's coming in to our flange of this B1 column. If we had this spun around, our holes would be facing to the outside of the structure.
Where they don't
we
do
would
us
have
any
just
good.
spun it 180 degrees. So
Right.
if we're not being mindful, looking at the print to our configuration, to our hole layouts, on our steel, we can make errors. And I love it when you guys do it, because y'all get upset because now you realize that you got to take everything apart that you just put together and spin the column 180 degrees. But it's a good lesson to learn, because you can see that if we're on a crew that's got 5 people standing and we've made this mistake, it may only take 1 or 2 of them to fix it. But yet I've still got 5 standing and watching,
Right.
because they can't move forward in the process until this column's in its right orientation. So if that would take 2 guys an hour to accomplish, I just spent 5 hours of labor for that.
Because we have people standing.
Right, and depending on where you're working, if you're working in New York City, you just paid, probably somewhere around $100 an hour
Per,
person.
right. So $500. So
$500 for that hour that comes off your profit margin because you didn't have your head in the game and get the right piece of steel in the right orientation.
and then compound that with the labor you spent to set it the first time, which was wrong, then the labor to reverse it, and the labor you lost because they already should have been on another part of the job.
Right.
So we're paying 3 times.
Right, and I'll tell you, when you interrupt workflow, it'll take you 15 minutes to a half an hour to get that crew back where they were before the stop.
Yeah, where everybody's firing on all
Because what
cylinders.
happens is everybody breaks off, lights a cigarette, goes to the water can or the Little Orange Shack, and before they come back, maybe 45 minutes longer's gone, or
Right.
maybe it's right before lunch and they say, screw it, we'll just get back to it after. I mean, these things happen every day, multiple times a day on your job sites, and you can just watch your profit margin can roll right off the job with the rain.
Right.
Okay, guys, I want to talk a little bit about how we rig the columns in the lab. You guys can watch video after video of steel being set, and I would suggest you do it at some point just to see how the professionals handle steel when they're flying in maybe 3 or 4 structural members at one time. But in our lab, we're only going to lift 1 piece of steel at a time, and we're going to do it a very specific way. We use, for steel, it's appropriate to use this cabling. So metal wire rope. And you can see these are in a choker format. Mark, if you'll let me have this one.
Yep.
I'll step into the camera. So we have loops on the end of a single cable. All right, this is a very handy tool. We use steel to steel. It wouldn't make much sense to use cloth strapping to lift these. I've seen it done, but I don't like it because a lot of times this steel will have burrs on it that they miss at the fab plant. And when you have a burr and those straps might start to slide up the steel or something, it can catch and cut the strapping.
Yeah.
And regardless of whether it's the wire roping or it's cloth strapping, once you get a nick or a tear in that strap or that rope, you got to discard it. It's got to be decommissioned and gone. And I mean gone.
Which usually means cut into pieces.
Cut into pieces.
Because we've all seen it where it's got a slight tear, it gets thrown into the dumpster, and somebody fishes it back out, and it's right back on the job site the next day.
Ladders, tools, everything. When you decommission something, especially if it has your name on it. Mm-hmm. Because remember, if your name's on it and it goes to somebody's house and they get hurt, you could get sued. So, cut it into multiple pieces so they cannot resurrect it and use it again. Best practice.
Makes sense. I notice we've got some kind of tag here.
Yes, all rigging, proper rigging, all safety equipment should have a tag on it that explains its parameters. And you can see here,
we have a straight configuration, which is the loop going right to the hook of the crane and straight down, and it gives us a 1.4 T, 1.4 tons, and that's in the vertical orientation. We have a choker, which is the cinch method.
we'll show them that.
And that is 1.1 tons in a choker. And then we have a basket configuration, which happens to be the strongest at 2.9 tons. There's always a pro and a con to which configuration you use
Right.
and which circumstance you're in.
Right, so if we're slinging loads of stuff, I do not like the basket configuration under any circumstances. I just don't like it. Because you're hooking both of your loops to the crane like this. If you lay something in here and the wind catches it or something, because remember, it's just a big pendulum in the air, stuff can fall out of that cradle. I don't like it. What we use in construction, what I was taught to use and what I've seen is the choke method. And that's one loop through the other, and it comes down and it cinches to the material.
So as you draw up, it tightens that
Right,
noose
as the weight
down.
hits it, it brings it down onto itself.
Yep.
That's the safest configuration for most of your applications. Now, I'm not saying that there aren't applications with a basket,
Absolutely.
but I just don't like them, and I never allowed them on my site unless somebody had a specific job that had to be done with it.
There are professional rigging crews that's
Absolutely.
what their job
Well-
is to go around and figure out the loads, the best way to raise those loads, whether it be from a crane, a helicopter, you
Yep.
name it, and that's what their job is.
Typically, most of your workforce is trained, has to be certified with rigging. I won't go into the union, non-union scenario, but training being what it is, if you have a setting crew that you're in charge of, get them trained in proper rigging techniques if they don't carry a certification already. Because one thing, when you lift a material into the air, you put the entire job site at risk. And if you're not cognizant of what's going on, you can hurt a lot of people quickly.
Right.
And time after time after time, it's proven.
So part of that certification process is inspecting all of your gear
Right.
before you get started.
So whenever you're using any safety equipment, and I call rigging safety equipment because it needs to be used safely, right? There are safety parameters that we need to adhere to. And the first is we always inspect our equipment
I don't care if it's a harness or it's lifting equipment, whatever, we check it out. Do you check your power tools? before you-
Absolutely.
We always check for cords and nicks, because if it's short, you can get electrocuted, and that's no fun. With our rigging, if there's a fray in this rope, like a cord's been snapped and you can see where it's broken and sticking out, this has to be cut and gone.
Right.
Because what we've done is we've taken the integrity of this, the structural integrity of this, and out the window.
So we're looking
because
f-
now it's diminished.
Right.
So now it won't lift the 1.1 ton we need to choke this column or a beam and lift it into place.
And we don't know. We can't make an assumption of
and-
what
and-
the capacity is
And
remaining.
the engineer won't tell you either, because their liability is in this piece of equipment.
Right.
So once it's damaged, they remove their liability from it, and so should you.
And we'd also, in the case of wire rope, we'd be looking for rust, anything that might indicate there's something wrong with this piece of
Right.
rigging.
You know, the best thing to do is, what I always tried to do when I was bidding work was to incorporate this equipment into my bid. Not just as overhead, tool overhead, and da-da-da, but I would, if it was an essential piece of equipment, I would buy it new for the job.
Sure. That way we know we're kind of in a clean start.
Right, because what they do is they want, if you have a contractor, smaller contractors tend to use their equipment past its time,
Right, because it's a cost.
because it's huge cost. It's a huge cost to a company, but if you incorporate that into your bid, because if you have the right equipment, I can bid my work more efficiently. I can trust my workforce to get the job done quicker with the right equipment.
Yeah, fewer breakdowns.
Fewer breakdowns. So if you make it just normal to have the equipment you need and new or proper on the job when you need it, you cut out all those 5-hour hits to your profit margin.
With the wire rope, we'd also be looking for things like kinks or
Kinks.
bends, right? We don't have to worry about that with the fabric so much, but if we had where a crease had been put into the wire rope permanently, that's now a weak spot.
Right.
So we'd have to eliminate that as
Right.
well.
Yeah. Now you'll see the kinking if a structural member is, like for our purposes, we'll buy new this summer, but we're going to use a choker that's got some kinking in it.
So we know that according to our load tag, we can hold 1.1 tons.
Ton.
So over 2,000 pounds. We talk through, this is a W8 by 10
Right.
at 14 foot long. So we know it weighs 140 pounds. So we're talking less than 10% of the capacity of the wire rope.
So in the lab, we can do that.
Sure.
On your job site, you don't want that. I don't care if you have a 1/2-inch choker that's all kinked and it can lift the world, and we only need to lift 140 pounds. I don't want to be the person that gets hit because it fails.
Right. It only takes a split
Right,
second for an accident.
and over the years that I've worked in this industry, I have seen the most bizarre things happen. And what it's taught me is the unexpected, the unexplained,
The unintended.
the unintended. If it can happen, it does.
Right. Yeah, we're working in an uncontrolled environment.
Absolutely.
We're working in conditions that may not have the best footing, may not be the best weather. It could be very crowded where we're working as far as the amount of workers per square foot on the job site. There's a lot of variables going on, and we're trying to eliminate variable when we talk about these things.
Well, let's talk about a big job and see what's going on. I mean, the biggest job I was on was a high school job down in Indianapolis, Warren Central High School. We had almost 250 people,
Sure.
not to mention summer school. And if you're going to take steel over a building where there are occupants and you can't schedule them out, I had to create lift zones. So I had mapped out on the roof of the school the only place we could run steel, because once you got over that roof, you couldn't drop it anywhere off the other side. So
Right.
your rigging had to be proper. Everything, you know, the operation was just so fine-tuned so that you didn't run the risk of injuring anyone.
Testing all your communications, having your spotters all set up there. It's a very extensive pre-planning.
It is, it can be a ballet, really can, where it's just these incremental moves, but they all have to be choreographed so that you can get your job done. I mean, from entering the roof, you had 10 foot where you could bring a piece of steel onto the roof.
Got to hit the window.
Man, I'm telling you.
Okay, let's get into actually rigging of the
Okay.
column.
So what we're going to do is we're going to run a choke so that we can pull this column up into its vertical orientation. So we've got a little, what we call a lifting lug. It's really just a clamp that we use on steel so that we can put eyes, you know, the threaded bolt eyes.
Right.
And then we'll run cable around that and use that as safety railing when we're up on the deck working on the second floor. of the
After we've
structure.
started
Once
going
we've already
up.
done the first up, but we can use it as a lifting lug as well, so it serves two purposes. So I've tightened this onto the beam, and what we'll do is, you can see that I've got a choker, and I'm using a choke configuration. Bring it up, and I'll cinch it up on the bottom side of our lifting lug.
And that gives another place for the wire rope to kind
Right.
of have purchase on the piece of steel.
Right. So if I'm lifting vertically, what I don't want to happen is this cinch up and lift it up so high, and then as it binds down, it starts to loosen up a little bit or something, and it starts slipping up, and then you can lose the member. So we have to have something that's going to keep this from sliding up and off
Makes sense.
and losing it.
So here we have the headache ball.
What we call the old headache ball on the crane. This one is kind of a pulley system, double cable instead of a single cable going up. But we have a hook hanging off, and then we have a rating. So this crane in the lab is rated to lift up to 2 tons. So it'll lift 4,000 pounds, not real fast and not real far, but it'll do the job. But it's good for what we do.
Let's go ahead and
All right, why don't you get
Lift the
on the
column.
controls, Mark, and let's get her up in place.
we'll talk about position of lifting with the ball. So we need to go.
So you can see I'm right over my rigging point, and Mark was over about a foot. So he's got to bring it right here, because when we rig a piece of steel, we want to be as close over the point that we're picking at so that when it comes up, it doesn't slide towards it. A lot of times guys will get off center, just rig it, turn around, start to walk away, the crane lifts it up, and because it wasn't over the load it was lifting, it drags the load to where the center of the cable is.
You're just creating a pendulum at that
Right,
point.
so it swings in, you get cracked, and you get hurt. So we always want to rig as close to over the point as possible. Okay, let's bring it up, Mark. There's another thing right there. You saw how the cable flipped off? That's because it's kinked. That's something else you fight with crappy cabling. Okay, let's bring it up now, Mark.
Good.
Yep.
Coming up. So we've got our column placed on our anchor bolts. We still have the crane rigged at the top. That's a little bit of a safety procedure. We can kind of hold the top of the column. I'll go ahead and move it in just a hair to help Scott balance it. He's going to go ahead and get the nuts put down. That'll provide a little bit more stability, and then we'll get ready to plumb the column north, south, east, west, and tighten up the connection nuts at the bottom.
Okay.
Can you show me, do we need to come towards me at all? Or are we all right to make adjustments?
We're good now.
Okay. All right, you ready? So right now I'll be reading the level and trying to hold plumb in my east-west direction while Scott's working with the metal shims down below. This is to help create the 4 points of contact at the bottom of the column. So my job is just to watch the bubble and try to hold it as close to plumb as I can get.
So we're shimming the 2 points of contact we need to give us our 4 so that she'll stay in place. This gets to be kind of like a Jenga puzzle.
I'm giving you a perfect bubble to work with, Scott.
Of course you are. Okay.
Tightening down.
Okay.
We can check our configuration, and we still have some play in the top of the column that allows us to pop in the beams as we go. And that's what we'll head to next.
Okay. Okay, let's get some bolts.
Okay. Again, I'm trying to get the crane ball or the headache ball as close to the center lifting point as we can get. That way we know we're trying to get a nice, good, even lift. So I'm just making small adjustments to the crane, and then we balance everything out. In this case, I can go ahead and kind of stop the crane ball from swinging and just see if we need any small adjustments. Even 6 inches will make a difference once we pick up the load. If we're off center, the load's going to want to pull one way or the other, just like on the column. So we try to make some little adjustments and make sure we're ready to go. Looks like I need to go. Try not to watch your head, Scott. Looks like I can come back to you a little bit.
Yeah, you're pretty close, Mark, actually. Okay,
That look good?
well, let's try this.
All right, coming up. So we'll just kind of test the load before we get it too high in the air. Scott found the center point with the cinch, and you can see how we're just kind of hanging nice and level or balanced. Makes our job a lot easier when we go to install. All right, coming up.
Let's go. Okay, not too high because I'm gonna have to go in.
Yep.
Okay, so
Now we're going to swing. Coming in.
okay,
come down a little bit.
Okay, now
Scott?
bring her up, Mark. Bump it.
Close.
Okay.
Okay, I'll get some drift pins. Scott's got his drift pins in. I gotta lower down a little bit. I'll go ahead and hold a pin for Scott while he gets a bolt and a nut put on. That gives us a little bit of a margin.
Okay.
Okay, so pull that drift pin. And now we'll go ahead and lower down just a touch.
Beautiful.
And go ahead and hold those pins for me. See, we're using drift pin. We've got a wrench on one end. We've got basically a giant threading needle on the other where we can put it through our bolt hole pattern and pull the two steel pieces into alignment by tipping the pin in and out. Gives us a different diameter to work with, and we can use it to steer the two holes together or line them up, and in some cases 3 or more, so we can slide our bolts through. Need a little bit of adjustment there. We good. Gonna make it.
There we go.
Got it? Okay.
Okay.
We want in or out? Out.
Out. Yeah, that's good. Okay.